Hey, Roger, this is Bill.
Hi, Bill. Good to see you're online.
Good to hear that it's working. Yeah.
Right. That's sort of what we all are wondering about right now. The people are starting to show up.
Roger, can you hear me? Is my audio quality okay?
Roger, can you hear me fine?
Yes, I can.
Okay. Jen, I can hear you.
Oh, you could? Do
Yes.
I sound okay?
Yes,
Okay.
you're
Okay.
slightly quiet, but not too bad.
Okay.
You are sort of quiet.
Okay. Is this better?
Yes.
Okay. Maybe I can turn this up just a little. I don't sound distorted.
No.
No.
Okay. Okay, great. Thank you.
Hi, Roger. Can you hear me?
Yes, I can.
Okay.
And Jen, shall I be the one who does the advancing of the slides?
Yeah, I think that's great.
So we have about 5 minutes more till we get the start time. Mm-hmm. Oh, good. I see Kris Davis, but I don't see your microphone, Kris. Okay, and I do see it.
And I think we'll wait just 1 or 2 more minutes and then get started.
Mhm. Okay, right now I think we have about 50 people so far, and so I think we could get started. And so we'd just like to welcome you to the webinar we have today, and Jen Braid will be our MC.
Good morning, everybody, and welcome to our webinar on progress toward 50-year lifetime PV modules using differentiated packaging materials and module architectures. My name's Jen Braid. I'm currently a research assistant professor of materials science at Case Western Reserve University and a visiting researcher at Sandia National Laboratories. I'll be introducing the speakers and moderating the Q&A sessions for today's webinar. This webinar is hosted by the Solar Durability and Lifetime Extension Research Center at Case Western Reserve University, and today we will hear talks on a variety of topics related to the manufacture, characterization, and degradation of PV modules with differentiated packaging and architectures and materials. Can you go to the next slide, please? Our speakers include partners from our current DOE-funded project to optimize double glass and glass backsheet PV module designs for degradation rate, mechanical durability, and cost, as well as experts in PV cell degradation and metrology. We will have 2 question sessions, one at the end of each hour of the webinar, and please enter your questions into the chat. And if you could include the name of the speaker that you'd like to answer them so they can be answered appropriately. The registrants for today's webinar span all levels of the PV value chain, including research, manufacturing, materials suppliers, and power plant operators from all over the world. As a group, you've indicated a variety of interests, with the most popular choices corresponding with industry relevance and trending new module technologies, including bifacial modules and PERC modules. This webinar is designed to be informative to the attendees regarding current research in the durability of double glass and glass backsheet modules, and also serve as a feedback mechanism to direct our future research in this area. Your engagement in the survey, questions, and feedback after the presentation is incredibly valuable to improving the quality of our work, and we will incorporate your suggestions moving forward in order to make a more highly impactful and industry relevant body of knowledge in the area of degradation science. So thank you all for your input. And with that, I'd like to introduce our first speaker, Roger French, who will introduce the Towards 50-Year Lifetime Modules project. Roger is the Kyocera Professor in the Case School of Engineering at Case Western Reserve University. He came to CWRU in 2010 after 25 years developing materials at DuPont Company in Wilmington, Delaware. So take it away, Roger.
Okay, great. Thank you very much, everyone, for coming to our webinar about our Towards 50-Year Lifetime Modules. And so what I'd like to do first off is just acknowledge the Department of Energy SETO program under our agreement number 8550. In addition, we'll have a presentation by Kris Davis of University of Central Florida from work that he's been doing in a different SETO project, 8172. And we'll also have Greg Horner of Tau Science discussing the PV characterization tools that we've been using in our system. So the people here are at Case Western Reserve University, these ones right here. At Canadian Solar is another one of our team members. DuPont Company is one of our team members. People at Cybrid Technologies who do the packaging materials, and also at NREL, Nick Bosco. So this Towards 50 project that we have, we're just in the a little bit before the halfway point. And what we've been doing is wanting to identify strategies to extend the module lifetime to 50 years by figuring out how to reduce the power degradation rate to 0.2% per year by relying on improved packaging materials and module architecture. So that would be comparing discussion of glass backsheet modules versus double glass modules. These are all in service to get to the 3 cents a kilowatt hour sunshot goal for 2030. The proposed work that we have actually involves both fabrication of mini modules, MMs, which is done by both Canadian Solar and Case Western Reserve University, the packaging materials from Cybrid, Weibull analysis and FEM of cell and mini module fracture done by NREL, exposures, stepwise evaluations at case, data analysis, and cross-correlation. So our real objectives are using these 4-cell mini modules to optimize double glass and glass backsheet design based on degradation rates, mechanical durability, quantify the degradation modes in these and see if there are differences between them, and be able to cross-correlate between the outdoor and the indoor results. So we'll be showing you the results to date in our project, but of course the project isn't over, we're just in the midpoint. So we've been fabricating mini modules here. There's actually 2 different geometries because of the 4-point loading that we do. We do exposures and stepwise evaluations. So this would be the 4-point bit loading of the 4-cell mini modules. This is our ELPL system that was developed with Tau Science. We then get into our data analysis and modeling, and then cross-correlation of the indoor and outdoor. So one of the things that's going to be unusual is that this is a statistically designed study protocol. So for example, looking here at the mini modules that we're doing, for example, for indoor exposure or outdoor exposure, there are 4 different sets. And there are then in set 1, which is what we have results to report on today, there are 4 different variants in set 1, and there are 6 made by SDLE and 6 made by Canadian Solar. So that means that we actually have variants of who built the mini modules. Are they double glass or glass backsheet? Did they use EVA or POE? In this program, we're using all multi-crystalline silicon PERC cells, and these are mono and bifacial cells. And so what we actually do in our study protocols is that we take these 20 total mini module variants, that's 5 different sets of mini modules over here, and 4 variants per set. That would be the versions 1, 2, 3, 4. And we then go looking at the samples of these. So there's 12 samples of each variant, 6 from CSI, 6 from CASE. We deploy them outdoors and indoors, and then use common characterization tools across the indoor and outdoor exposures. So what we have is that these variations and these small sets of 6 or 12 samples of each variant are ones that set us up to be able to do statistically informed findings instead of just one-off observations. So in the set 1, we're looking in monofacial multi-silicon PERC with transparent EVA and POE. The back cutoff is a UV cutoff encapsulated behind the cells, glass backsheet and double glass, and the numbers right here. And the indoor exposures that we're doing are modified damp heat or modified damp heat with full spectrum light. So these basically mean that we've designed the number of mini modules to be set to be able to get statistically significant results. Out of those 48 mini modules in a set, we actually make square ones, 32, versus 16 to enable the cell mechanics work. Okay, we also take another step here in terms of the data handling, that we string and tab the cells in the mini modules so that we can measure both the string of 4 cells and we can measure each cell individually. So you can actually get 5 electrical measurements out of each mini module, each step of the way. We then measure them at baseline and at 5 steps through time. So in the indoor exposures, we'll have 6 time points overall, whereas outdoors, it's easier that we can take literal time series IV and PMP scans, where we scan the IV curve every 10 minutes and we get a PMP every minute. So the fabrication, for example, here a case is done with our laminator here. This is the geometry of how we're wiring them up with these 1-wire junction boxes, so we can connect to the full string of 4, or we can do each cell individually. And in addition, in the cell mechanics part, to look at sensitivity to cell fracture, we made 121 cell mini modules. And again, we have oriented the bus bars and grid lines differently. The exposures that we're doing here are all with modified damp heat, where we're only heating to 80 degrees centigrade. And this is chosen so as to be below the glass transition temperature of PET, and to therefore avoid some of the aggressive corrosion that is really only seen in full damp heat at 85C, 85% relative humidity. In addition, when we do the modified damp heat in full spectrum light, instead of a UV light exposure, this is full spectrum light, about 420 watts per meter squared irradiance, so 0.4 suns. So that means that we will have current flowing through the mini modules during exposure. And then we do 5 exposure steps in total for about 2,500 hours. So it takes us about 4 months to go through a set. Here's what the outdoor setup looks like, and we'll be seeing results from the outdoor and indoor later on in the webinar. And so these are all the mini modules set up here. And then in this box, we have our Daystar controller and load units. So these are being exposed at our sun farm on campus. And we've got so far 9 months going, and we're collecting our time series data. So we can collect similar data on paired modules indoors and outdoors. Characterization, as I said, so Spire Solar Simulator, the Xinjun Suns VLC, our EL and PL camera system, and the 4-point loading for cell mechanics to look at the cell cracking possibility. And we do all baseline measurements initially before exposure, and then take them stepwise through time. In addition, out of the approaches that we take, we've developed a number of different software packages that are available to people in the community. So one for identifying what Köppen-Geiger climate zone you're in, the structural equation modeling, so NetSem for SMR models, data-driven IV feature extraction, SUNS VOC from the time series IV curves. This just published in June. There's another one that's on PV image, and so this is for image processing of EL images, and PVPLR is in review right now with CRAN, and that's for calculating performance loss rate. In addition, we have a set of open data sets available to anyone on our SDLE OSF page, and those include both time series data from the DOE RTC systems and also EL images. So as we go through today's webinar, we'll see more results and hear more about it. I hope you enjoy.
Great, thanks, Roger. So our next speaker is Kunal Rath, who will give us an overview of current PV module warranties. And Kunal is currently a PhD candidate in the macromolecular science department at Case Western. Kunal?
Thanks, Jen. Looking at what the warranties that exist in the companies that are producing the most up-to-date modules is useful to give us an idea of connecting economics with updates in technology. Can we go to the next slide? So there are a few different types of warranties that companies will identify. And so these give us different types of information about the module technology. Product warranties are standard, more or less, amongst the industry because they deal with the actual components of solar panels failing and replacing product failures. So this is pretty similar across any other kind of industry that would offer warranties on their products. Performance warranties are particularly interesting to us because they deal with long-term degradation of the product. So these are values that companies will guarantee for power performance, power production in the first year and over the course of the life of the module. Labor warranties are also interesting to look at, because we can see, and we are seeing more often nowadays, that companies are noticing that the method by which PV systems are set up and installed has a significant impact on their lifetime. Next slide. So this is a list of some of the most up-to-date modules offered by companies today. And so we can see the products offered in the years 2017 and 18 compared to the products offered now. And so the two types of updates that we can see with companies like SunPower and REC, the main update that they have is a change in cell technology, usually coupled by a change in module design. Whereas we can also see with a company like Hanwha, the main thing that they update is their product warranty while they're using the same cells and more or less the same module design, which we can see in the next table on the next slide. So here, the Hanwha Q-Peak Duo Black G6 Plus is the most up-to-date model that they have for their quantum cells. And though they're using the same kind of monocrystalline quantum cell technology, they've updated their product warranty to be competitive in the market. So that's more of an economic decision. In terms of the effective technology on impacting these warranties, we can see the REC and SunPower most recent updates bring their annual loss percent in performance, their performance loss ratio to be about 0.25%. And so these numbers are extremely important to us, especially considering this kind of project, because these are the numbers that represent that approaching 50 years as a lifetime for modules is a realistic goal. Next slide. So there are a few unique things to notice about these different major companies and in the ways that they offer their warranties and the ways that they've updated their warranties over the years. So SunPower boasts the strongest warranties of most of the modules that exist in the market. They talk about their unique connection strategies and how that improves their degradation time. Hanwha bases their warranties off of their cell technology, and so they use similar warranties across different kinds of cells, even across different kinds of module designs. And that's the strategy that many companies use. But companies like CSI base their warranty specifically on the cell type and the module design and all the different factors that go into module production. So we see many different kinds of highly specific warranties for the different products that they produce. Next slide. And REC offers, this goes back to talking about labor warranties, an interesting table where they compare the warranties that they offer if you use any installer versus installers that are certified by REC. And this is something that's important to notice because PERC cells in particular show a greater loss in performance over the first year as compared to following years. And although we know that that is related to the degradation that occurs in PERC cells, it can also be significantly correlated to the experience of the installers when putting in the panels to begin with. So that could be a potential area in which to decrease the first year degradation. Next slide. So looking back, the ITRPV International Roadmap for Technology showed these are their predicted decreases in warranty, or sorry, decreases in degradation and increase in warranty as we approach 2030. And we can see that a pretty significant trend that they seem to predict is that they think that degradation per year is going to sort of plateau at 0.5%. And so that number already we're seeing isn't necessarily accurate by SunPower's A, E, and X series modules and REC's heterojunction technology modules, where they're saying that their degradation percent annual loss is around 0.2% or 0.25%. Next slide. So here are some results from last year when we did this kind of warranty study. So this is comparing different kinds of cells. And so we can see that the first year degradation values more or less match what we see today. So 97 to 97.5% of nameplate power after the first year. And then we're seeing this annual degradation of about 0.5% annual loss, which is what ITRPV is reporting as the sort of plateau value. And so that matches the idea of a 25-year product warranty or 25-year performance warranty, because 0.5% per year will end up with an average or a lifespan of about 25 years. So we want to cut that number in half to get it to 50 years. Next slide. So this shows that the companies in 2020 are seemingly able to do that, mostly with changes in their actual cell technology. So SunPower and REC, with their updates in their module design, are able to achieve those numbers of 0.2 or 0.25% annual loss, whereas Hanwha, which is using the same cells, is seeing the same kind of percent loss per year, though they have updated their product warranty. Next slide. And so in terms of first year performance loss, we're still seeing more or less the same kinds of values that we would see in 2019 or 2018 or 2017. where companies are still promising about 97 to 97.5% of their nameplate power after the first year. But this idea of installation having a significant impact on power, especially in the first year, could be a way by which this value can be decreased without necessarily having to improve the technology that's present in the cells. So that's a general overview of where warranties stand in the PV industry today.
Great, thanks, Kunal. Our next speaker is Laura Bruckman of Case Western. She will discuss the current PV market share of glass backsheet and double glass modules. Laura is an associate research professor in the Department of Materials Science, developing predictive lifetime models for materials degradation related to stress conditions and induced degradation mechanisms evaluated by quantitative spectroscopic characterization of materials. Thanks, Laura.
Thanks. So next slide. So this section, we're going to talk a little bit about the direction of PV modules as a whole as we move from glass backsheet modules to glass-glass sales. This graph comes from Canadian Solar, who is a partner on our project. And this talks a little bit about what they're seeing in their current and previous sales. So the table shows the sales of percentage sales of glass backsheets versus glass-glass modules. And as you can see, from 2019 to early 2020, most of the modules sold are glass backsheet. What they've seen recently and their sales is that their new products have switch percentages, where now they're selling a majority of glass-glass modules with less glass backsheet modules. And this happened quickly. So the change was very, very quickly. And they see this as also something that will continue to happen just because as we make larger and larger modules, larger wafers, the glass-glass design allows for a little more mechanical reliability for these modules, therefore making the glass-glass modules the chosen design. Next slide. So this comes again from this International Technology Roadmap for PV. So these four graphs will start in the left-hand top quadrant, talks about the difference between full cells in blue and then half cells in yellow. And as we move to 2030, they see that we start increasing in half cells. So that we're going to have different types of cell technology as we move closer and closer and kind of decrease the amount of full cell modules created. As we move to the right-hand top quadrant, what we see there is that PERC cells begin in 2027 to basically be the only cell technology or completely reduced ALBSF cells. So we're removing ALBSF cells from the sales and going completely to PERC. And then we have some more increase of these other type of technologies like heterojunction cells and some back contact cells. So the new technologies are going to start increasing, but will basically majority will be PERC cells. On the left-hand bottom quadrant, we are talking about bus bars. So basically in after 2020, there's no longer going to be these 3 and 4 bus bar modules. And we will be moving to 6+ bus bars, which is in the yellow. But that will also be decreasing as we start having, or 5 bus bars will start decreasing. We're going to move to 6 bus bars in gray. And then there are also going to be things like shingled celled or multi-wire technology increasing through time. So the way that we're stringing these cells together is changing along with cell technology. And then our last graph in blue, it looks at EVA as an encapsulant. Right now, that's been the dominant encapsulant for decades. What you can see here is there's a much slower change from EVA than anything else we've seen to polyolefin, which is what's predicted to be the encapsulant that's going to take about 30% or so of the market in 2030. And then there'll be some additional encapsulants that are not quite there yet, but we'll still be seeing a majority of EVA in 10 years. Next slide. And then this talks about the difference between glass backsheet versus glass. So the T50 project focuses on a lot, what's the difference in degradation between these two types of modules. And what we see here by 2030 is that there will be a 30% market for glass modules. However, industry often hits these roadmaps much earlier. So we can potentially see a larger market share of glass backsheets in our future. So thank you very much.
Great, thanks, Laura. And next, Bill Gambogi of DuPont will tell us about transparent backsheets using clear Tedlar PVF films. Bill is a technical fellow with the DuPont Photovoltaic and Advanced Materials business. His work focuses on photovoltaic materials and their impact on PV performance and durability. Bill has worked at DuPont for more than 30 years and has been involved in several new product developments in the areas of optical, electronic, and optoelectronic materials and devices. He has contributed to over 30 patents and more than 30 technical publications and regularly delivers technical presentations on reliability issues in photovoltaics at international technical conferences. Thanks, Bill.
Thanks, Jennifer. So thanks for the opportunity to discuss transparent backsheets using Tedlar films. These are our backsheets that we have contributed into this program, and I'm going to give you a little bit of background on the performance of those backsheets. Next slide. So a lot of people are familiar with white backsheets and Tedlar backsheets that have been in the field for 30 years. Not many people know that transparent backsheets have actually been in the field for almost 20 years. Here you see an example from a building in Amsterdam. They've mostly been used in BIPV type applications. We continue to look through our field program at the performance of transparent backsheets in the field. But for this particular installation, we saw no particular issues related to the backsheet. So that's encouraging. Next slide. A little bit about what the advantages of a glass backsheet module are. So clear Tedlar has a very high light transmittance. It has, as we showed there, long-term field-proven performance, has excellent weathering resistance, long-term UV protection, excellent mechanical properties, which are needed to avoid failures in the backsheet, anti-soiling and easy cleaning, salt mist, and chemical resistance and sand abrasion resistance. I'll be showing you some data on these. Next slide. Here is the PVF film, the performance of the PVF film. It has high transmittance in the wavelengths in the visible where the silicon cells are sensitive, has low transmittance in the region where the PET could be damaged by UV. So it has high transparency, good mechanical properties, and excellent UV protection of the PET core. Next slide. Here you see the performance of the film. You see its UV absorbance, the stability of UV absorbance. It has stable color when exposed to UV. These are exposures under xenon arc. It maintains its mechanical properties, so it's not going to crack, and has stable light transmittance, so you have high power on the bifacial module. Next slide, please. There's this a representative structure, so it's Tedlar, transparent Tedlar on the back side, a core PET film, and a coating on the inner layer. Here you see the performance of the backsheet, high optical transmittance, and very little change in yellowness. Next slide, please. Here's an example of stable mechanical properties. So on the upper part, you see exposures to UVA out to beyond what would be reasonable for a 30-year product for a bifacial module, out above 400 kilowatt hours per meter squared, and the elongation is stable. elongation is also stable out to 3,000 hours in the chart at the bottom. Next slide, please. One of the considerations is mechanical properties for a backsheet. We have seen in the field PVDF, for example, cracking out at anywhere from 5 to 10 years. Here's some examples of PVDF. The issue there is the TD elongation. So we've looked at 4 different PVDFs, actually over a range of temperatures down to minus 40 degrees C. And what you see is, well, very low TD elongation, even at room temperature, but down to 40 degrees C, it continues to drop while the Tedlar maintains those properties. So that's important in lots of applications where the temperature is varying significantly. Next slide. We've looked at other material, other transparent backsheets, and this is at a highly accelerated metal halide exposure, and we see for other materials not such good stability in terms of mechanicals and color. So that's a concern. Next slide. Here's some information on dirt, detergent, and salt resistance. So we've done testing by standard ASTM methods and seen good performance for the Tedlar film. Next slide, please. We also see excellent solvent resistance for Tedlar. There you see a comparison of a Tedlar-based backsheet, an FEVE coating-based backsheet, and PET, and very good resistance for cleaning that could be important in manufacturing and for cleaning in the field. Next slide, please. There is some concern about abrasion resistance. So here we look at falling sand type exposure and compare to other transparent backsheets. So you see very little change in light transmittance for the Tedlar-based backsheet, some loss in both FEVE and PET, and the volume for sand wear out is high for the transparent backsheet. Next slide, please. In terms of performance in bifacial modules, here you see data from a tier 1 module manufacturer where they've gone out to 600 thermal cycles. Again, they're looking at the front and the back side performance. They're going out to 3,000 hours in damp heat, going to 3 times the IEC qualification requirement for TCHF, and then going out to 192 hours for PID. All of them well within the range that is expected for qualification. Next slide. We've also looked at commercial glass and glass backsheet modules in terms of their resistance to PID. So here we've gone out to 96, 192, and 384 hours of PID stress, minus 1,500 volts at 85 and 85. We've looked at the front and the back and looked at modules. These are 60-cell modules that are made from exactly the same BOM, the only difference being a backsheet versus glass. This was 2.5 millimeter glass. And what we saw was a significant difference, particularly on the backside for glass modules, more loss in glass modules on the backside due to PID. These were also all using POE encapsulant. So POE will not completely eliminate the PID issue in glass modules. Next slide, please. We've also applied our MAST testing. It's a sequence of damp heat, UV, and thermal cycling. We've used it effectively to predict backsheet performance in the field and identified the issues with AAA and with PVDF in the field. We have also applied it toward our transparent Tedlar backsheet and seen good performance under that stress condition. That this methodology is also being adopted in a modified form in IEC to identify backsheet issues. Next slide. The risk with glass, the main risk that we've seen has been delamination. So the glass structure can entrap materials and lose adhesion. So here's some examples, and we, again, through our field program, we continue to look for understanding of how glass is performing in the field. It's a relatively, in terms of high volume, relatively recently adopted. So there's issues there. Next slide. We've also looked at performance in the field. Here is, again, from a tier 1 manufacturer, we're seeing appreciable differences in performance in the field. These are 4 different installations. And again, we're seeing higher performance with the glass backsheet. We think it's because of lower temperatures. So we're going out there and confirming that through modeling and through measurement. Next slide, please. And here you see the same one example of a field and tracking it over time, showing 0.83% more rear side power output than in the glass backsheet version. Next slide, please. The main improvement of glass backsheet and the main driver, one of the main drivers of glass backsheet is its lighter weight. So you see significant differences between glass and glass backsheet in weight. And as the modules get bigger, that problem becomes larger. Next slide, please. So just to sum up, what we see for transparent backsheet, it has a proven module structure. It has higher power output. It has lower installation because of the lighter weight, and it's a mature manufacturing process, so there isn't as much modification needed in manufacturing. So thank you for your attention, and I look forward to questions. Thanks.
Great, thank you, Bill. And that's a good reminder that we have a Q&A session coming up, so please enter your questions into the chat. And now Kris Davis will discuss manufacturing defects, failure modes, and degradation mechanisms in ALBSF and PERC modules. Kris is an assistant professor of materials science and engineering at the University of Central Florida, with secondary joint appointments in the College of Optics and Photonics, the Florida Solar Energy Center, and the RISES FET Cluster for Energy Research. His research is focused on the development of new materials, manufacturing processes, and characterization techniques to improve PV technologies and speed up the adoption of solar energy as a global energy source. This work is currently supported through multiple funding awards from the U.S. Department of Energy and from industry. Thanks, Kris. Take it away.
Thanks, Jen. Can you hear me okay?
Yes.
Yep, sound good.
Great, thanks. So yeah, today I'm going to talk about some different, manufacturing defects and kind of reliability issues that we've observed quite a bit on cells and modules that we've characterized here at UCF. And particularly, I'm going to focus on especially those kind of defects that you can easily identify with things like EL imaging, and show some of the signatures of those in some of these images. Next slide, please. So of course, as throughout this webinar, we've been discussing the entire supply chain, and there's things that can arise, early upstream that can cause reliability and durability issues, as well as those that, of course, that are a bit more obvious that can occur further downstream. So today I'll kind of highlight a few problems that kind of occur at kind of the wafer level, so kind of more of that feedstock crystallization and wafering. And then I'll spend most of the time talking about issues that can arise kind of at the cell level. And then I'll highlight a couple of examples of things at the module level. Next slide. So I kind of have a table that I kind of put together to kind of organize my thoughts on this. And so I'll basically walk through and try to highlight, the specific defect or failure mode, its point of origin, in terms of its position in the supply chain, how it influences the IV and SUNS VOC curves, and then, whether I think that there's much risk associated with that specific defect in terms of the reliability, right? Because there's some defects that will of course affect the cell or module, when you do the flash testing on the manufacturing floor, but then they may not actually be a problem once you put it in the field, like kind of what that point at t equals 0, that's all you have to worry about. But there's others that may, they may not have much of effect, initially, but then over time that can be more of a problem. It's a bit subjective, and we're still working through this. So any feedback would be much appreciated. Next slide. And so I'll talk a bit about, of course, the influence of these defects on the IV or JV curve, and highlighting specifically, whether or not it affects, like the JSE or VOC or the fill factor. And of course, the hope is to keep all 3 of these high so you can keep the efficiency of the cell and module high. Next slide. And one of the things we try to do is basically try to break down, different losses in efficiency to either optical losses, resistive losses, or recombination losses. And we do that by a combination of different imaging methods. So we use a lot of, QE mapping and reflectance mapping to look at particularly optical losses, but also to some extent recombination losses, because optical losses really affect the short circuit current, but recombination losses kind of can affect all parts of the IV curve. And then to look at recombination losses with a little more detail, we use like open circuit PL imaging, which doesn't really have resistive effects, but can easily highlight recombination problems. And then either electroluminescence or biased photoluminescence, where you're doing photoluminescence imaging, but you're also pulling current from the cell or module. That can be very valuable in identifying kind of resistive losses and things like that. So we use a combination of different luminescence imaging techniques and this kind of QE mapping to try and figure out what the actual loss mechanism is. Because if you have that coupled with the actual image itself, you can often trace the problem to a root cause. Sometimes it's not always the case, but often that can be very helpful. Next slide. So starting at upstream with the kind of the wafers and cells, there's of course multi and mono, and there's a number of different defects and failure modes. Some of those are quite well known, and things like dislocations and high recombination grain boundaries, and those of course affect the VOC of the cell. But ultimately, I think most people would agree there's not a whole lot of risk that those are going to be reliability issues in the long term. In the case of Czochralski wafers, you have oxidation-induced stacking faults, oxygen-induced stacking faults, which show up as like these kind of ring structures, which again can affect the efficiency, but it's not clear whether those are really a reliability issue or more of just like kind of a manufacturing issue. And then you have 2 defects that are very much a reliability issue: light-induced degradation, which has been studied for a long time. There's a lot of different ways to do repassivation, regeneration processes to kind of address that, as well as things like light and elevated temperature-induced degradation, lead-ID, or carrier-induced degradation. And that's obviously an active area of research. So a lot of that's going into that. So if you go to the next slide. So here's an example of like a multi-ALBSF cell where you can clearly see a bunch of these dislocation centers that I've kind of highlighted here that you see in the PL, which corresponds directly. So we basically generate these VOC images from the PL images, and then also using the kind of the QE mapping, you can see that they also affect the JSC as well. So those recombination centers affect both. And if you go to the next slide, it looks like the figure got kind of messed up here, but essentially what you'll see is that the base loss is where this shows up. So if you do like the QE analysis, it ultimately, it doesn't show up in the emitter loss, it just shows up in the diffusion length and the J loss B. So next slide. Oxygen-induced stacking faults, those also have kind of a clear signature that's easily visible, easily identifiable. It shows up as these rings, but again, I don't think this is really a reliability risk. I'm happy to hear more if that is the case, but it's something that you'll often see in different CZ types of wafers. In terms of LID and lead ID, those are kind of tricky because as far as I'm aware of, there's no real obvious signature if you just get a cell or module and you try to collect PLEL. It's more of something that is related to the history of that cell module in terms of the thermal history and its exposure to light and temperature, in different sequences. And again, the activation of defects and then the repassivation of those defects. So that one's a bit more challenging. So I'd be curious of any of the people listening, if there are ways that you can kind of easily identify this, but it seems to be something that you can't really just pick up just from a specific PL or EL image of a cell. Going to the next slide, please. So the other kind of common failure mode that's been studied quite a bit are shunts and junction kind of pre-breakdown. And so those can be an issue. And so that essentially is where you have like a current path through the junction. And so that can be the case in both, multi ALBSF as well as mono ALBSF, as well as PERC cells, really any kind of cell that has a junction. But it's especially, an issue when you have high temperature screen printed paste that etch through a dielectric and can actually consume some of the junction and punch through. So if you go to the next slide. So we have some examples here. It looks like this figure got messed up here on the left, but essentially these are different types of shunts. And so you can see at least the DLIT image where it shows like kind of a shunt here. And this was done in collaboration with NREL. But what we showed in this was essentially you have like these shunts do show up in the PL and as well as the open circuit voltage image, as well as the JSC image. But if you really want to have a good detailed look at, these kind of issues, thermography is a good way to go. And on the right, you can see examples of thermal images that we got from Tau Science, where you have the case of what I mentioned before with the overfiring, where you essentially have the silver paste, as it consumes the silicon nitride dielectric, but then it continues to consume some of the silicon. And if you overfire too much, it can punch right through the junction, and that can be a problem. Another manufacturing, kind of defect that you can observe is poor edge isolation. So often with like a diffusion process, it'll wrap around to the rear side of the cell, but you have to deal with that because of course that provides a similar kind of current path to the rear contact. So you have to do edge isolation. If that's not done properly, you can see that will show up in the edge. Next slide. So another one is cell passivation. And so there's different ways that the front and rear surface passivation can be, can have issues. So you can have poor emitter passivation. That's typically in the case of these kind of P-type cell architectures like ALBSF and PERC, that'll be a silicon nitride coating on the front. So there's issues that can happen during manufacturing, and then there's potential issues that can happen as these cells and modules are operating in the field, whether it's related to kind of UV degradation or damp heat, or some work that's been shown, like Peter Hackey and his team have shown that PID can actually, if you have really bad cases of that, you can get corrosion of the kind of front ARC and passivation layer, which can clearly be a problem. And there's also, of course, potential induced degradation and shunting, which also seems to be related to the front surface passivation. So sometimes that can be an issue where the fixed charge is changing at the surface, and the fixed charge is important because it controls the minority carrier concentration near that interface. And you can have other situations where the actual chemical passivation, the interface defect density is changing. So just depending on the mechanism, there can be different ways in which this can unfold. And this is another one that's an active area of research that we're actually working on right now with Roger and his team at Case Western and Canadian Solar as well. If you go to the next slide. You can kind of see an example of this, just kind of poor rear surface passivation in the case of a PERC cell. So this is a mono PERC cell here. So we have the PL image, which we converted to a VOC image. And you can see on the top, there's like kind of this dark region that is likely related to the surface preparation and then the kind of oxide nitride deposition on the rear side. And so it, of course, also shows up in the JSC due to the kind of the optoelectronic reciprocity. So things that affect, the VOC will often affect the JSC as well. And then if you do the analysis of the QE at each point, you can actually separate this into like whether it's recombination at the front or the rear. And in this case, it does show up as a rear recombination thing, confirming that it's on the rear side. So that's one way to do that. And so, this is one of those that's probably more of an issue just at the manufacturing stage, but there's also some work in the literature that's shown passivation can degrade based on exposure to light and temperature. And one of the big challenges right now, at least in the case, especially for like multi-perk cells, is separating when does the passivation degrade versus when does the actual bulk carrier lifetime degrade in the material itself. So things like carrier-induced degradation. So some of the degradation for surface passivation is also related to hydrogen. And a lot of people have said that a lot of the carrier-induced degradation is related to hydrogen in one way or the other. And so that can be a difficult one to suss out, but in the literature, there are some examples of how you can do that with very careful experimentation. But again, it's a challenging one to do, to just kind of spot these defects just using like a EL image. You almost need to know the kind of the history of the samples in terms of like their exposure to light and temperature. Next slide. So cell metallization. So you could argue the metallization and interconnection are, a couple of the areas where degradation is especially concerning. And this applies to both multi and mono, ALBSF, and PERC. And so some of the different, defects and failure modes, you have front contact grid interruptions. This is one that, everyone's probably seen if you've seen EL images of these types of cells. Doesn't have a huge performance penalty, and it doesn't really seem to have any kind of reliability risk, in my opinion, but I'd be happy to hear otherwise if that is the case. There's another feature that looks similar. It almost looks like an interruption, but it seems to stem from kind of a contact failure near the solder pad. So I'll show some examples of that one. And we're still kind of like really trying to understand that specific failure mode, but this one seems to be related to also mechanical stresses. And so this is one that we think there could be some potential risk there. It's mostly an issue for soldered bus bar cells as opposed to kind of things like, smart wire or shingled interconnects, but it's something that we'll bring up and we're currently looking into. There's also, of course, contact corrosion. This has been observed quite a bit with exposure to damp heat, with acetic acid formation when you have EVA packaging. So that's pretty well known, but we have seen different signatures of this in some of the work that we've done with Roger and his team, where depending on the type of paste and the frit composition that you use, the signature can look quite a bit different. So that's kind of interesting. And we think that could be related to the underlying kind of chemical processes that are going on at the interface between the silicon and the frit and the silver. And then you have rear contact voids that are only applicable, that are for PERC cells, and then rear contact corrosion is another one. So rear contact voids aren't really that much of an issue. I think early on, manufacturers were concerned about those, and we had some projects with manufacturers how to detect those. But I think people have found ways, using different printing methods and different paste and firing procedures to kind of avoid those rear contact voids. But I'll show an example of that too. Next slide. So front grid interruptions, a lot of you have probably seen this. So here's an example where we did, some biased PL imaging. So we have our open circuit PL imaging that we use to get the J0, the saturation current density, and you can kind of see that this highlights kind of those grain boundaries and dislocation clusters that act as recombination centers basically. And then when you do the bias PL, you can directly calculate the actual series resistance and get a map of that. And what you see are some of the rectangular dark regions showing in the efficiency map, which we also, we determine using a combination of these different PL imaging methods. You can see some of those dark rectangular regions show up as bright regions in the series resistance. And essentially that's commonly just a screen printing defect. So if you have, just an interruption where you have like a gap in the finger, there's no path for the current to basically travel. So you have this high resistance path for it to get back to the bus bars. And so that's a common one. Although, the actual impact on efficiency doesn't seem to be like massive, and it certainly doesn't seem to be like any kind of real reliability threat as far as I'm aware of. Next slide. I think that's a bit different from this one. So here you can see another example, and we see this one a lot, especially in modules that have gone through some kind of mechanical stress. And so if you look here, you can see similar like dark rectangles. I've kind of highlighted them in white, but they also occur in other parts of the cell. But you can see they can get quite severe, as the case on the left, versus a little less severe here. So what we think is happening is that where the finger goes and connects the bus bar, probably due to some kind of mechanical stresses, you're getting a separation of that finger from the bus bar. So now you can't, now current has having trouble getting all the way back to that bus bar. And so it'll often originate either near the solder pads themselves or kind of along the bus bar. And so we're doing quite a bit of work to kind of characterize this. And some of the work that we're trying to do with like machine learning, for example, we're trying to distinguish between those two because we think the fundamental reason is quite a bit different. In one case, it's probably a print defect. In the other case, it's probably related more to kind of like the stresses that are going on within the cell once it's encapsulated and put in the field. Next slide. And here's some examples of the front contact corrosion. I'll try to move quickly through this. So this is one that my understanding is you don't see in the field much, but when you put mini modules through damp heat for a very long time, you'll start to see this. And so it's where you have this darkening occurring, you know, from the bus bar kind of radiating out away from the bus bar. So when you do PL, you don't really see it. So we can kind of attribute this to a resistive loss. We have done some QE mapping and we see it doesn't appear to affect current collection, which is a bit surprising. We'd like to dive a little bit more into that. So maybe there still is a current path, it's just highly resistive. So we're still looking more into that. But if you contrast this, if you go to the next slide, you'll see more of the kind of the common way that you would think of in a lot of the literature where you see this type of contact corrosion where it occurs all over the cell. And so this one is the one that's a bit more problematic because it starts to happen earlier. And this one has been, you know, studied quite a bit, and it's related to that, again, that acetic acid starts to remove some of the lead oxide frit that's between the silver and the silicon interface. And so our understanding at this point is that, you know, depending on, it seems to be mostly an issue between multi and mono. And the reason for that is the surface morphology between the two are different. You have pyramids and isotexture in another case, and you have to use specific frit for the multi to make sure you have very good adhesion. It's hard to get as good adhesion there. So the frit that they use makes it a bit more susceptible to this form of degradation. And of course, the paste suppliers, is my understanding, they're very aware of this and they're working through ways to resolve that. But we're still trying to get a really good understanding of this versus the other mechanism. And the other mechanism we think may be related to some metal diffusion from the interconnect and then a subsequent kind of oxidation that results in like a delamination of the finger. So we're still trying to study that, but it's kind of interesting to see these, you know, these two completely different like signatures in the EL image that seem to be related to a similar kind of corrosion process. Next slide. And I mentioned the voids in PERC cells. So this is an example of a PERC cell where we did some open circuit PL and we also did some acoustic microscopy and some cross-sectional SEMs. And so there's different types of voids that you can have. You can have obviously a good contact where you have the, you know, you have the aluminum contact and you can see the BSF. You have some voids where the BSF's there, but the contact's not there. So you get some passivation from the BSF, but you don't have a current path. And then you can have voids without the BSF. That's kind of the worst variety because you have basically like, you know, no path for current, but also you don't really have a BSF providing any passivation. So doing combinations, you can detect this. But like I said, I don't really think this is something the industry is that concerned with. I think they've kind of addressed this issue, it seems. Next slide. All right, now the module level, there's of course a bunch of things that can go wrong. And I'll talk briefly about cell fracture and then interconnect failure here to wrap up. Next slide. So cell fracture, I'll give a shout out to Jaubert Senior and Eric Schneller, who worked with Andrew Gabor on developing this load spot system where they can do simultaneous IV curve measurements and EL images while modules are under mechanical loads. And so from that acts as a great kind of database to look at examples of what things can go wrong. And so working with Jaubert and others, we've kind of been looking at cracks and there's a bunch of ways to classify cracks, and that's very well studied. For our purposes, to keep it simple, we just have kind of these closed cracks, which I show on the far left. Cracks where there does seem to be some resistive effect. You see this gradient in the EL image that suggests there is this kind of resistive kind of you know, current flow issue that you can see here in the middle. And then you have the cracks that we have completely isolated kind of regions where it becomes completely dark. And so that's one way to characterize that. And so cell fracture is obviously a problem. And, you know, there's a lot of, that's already been brought up with glass to glass, and, you know, it's something that the industry is paying a lot of attention to. And then the last one I'll talk about, next slide, is interconnect issues. And so this is from an experiment one of my graduate students did, Dylan Colvin, where he deliberately kind of cut interconnects at different parts of the cell within a module. So specific interconnects were deliberately disconnected, and he did a bunch of experiments where he cut more of them over time, and we look at the impact on series resistance and also the signature of EL. So this one is pretty clear and pretty obvious when you see it. So you'll see this sometimes. And then we can also, by doing EL as a function of current, we can fit a curve and get series resistance, and you can see how you can, it shows up as a high series resistance in these regions. So this is another one that's a pretty clear and obvious defect when you start to see that one too. All right, and I think that's the last slide. Thanks. And then, yeah, questions, please feel free to post questions in the chat. Thanks, Jen.
Great. Thank you, Chris. So now we'll have our first Q&A session. Let's see. So thank you for putting questions into the chat. Let's start with one for Bill Gambogi. So Bill, what do you think could be the cause of PID and modules using PoE as encapsulants? This is from Chiara Beretta.
Yeah, it's good. It's a good question. We have seen it. I think that PoE is more resistive, but it's not, it's not completely insulating, even especially under the damp heat condition, where you're putting moisture into the encapsulant and potentially changing its resistance. I think from the backside, a lot of people are looking at impact to the passivation layer due to charged particles, and as we look at the difference between glass and glass backsheet, we're suspecting that maybe some charged particles from the rear glass could be participating.
Great, thanks. Let's see, here's a question for Kris Davis from April Jeffries. Regarding your reliability risk tables for cell fractures, the risk is high for PERC and ALBSF full and half cells. For wire and shingled interconnections, the risk is classified as low. Is this proven in the field, or is this from a logical reduction in risk based on the expected improvements from these technologies?
So I can't comment as whether, like, in the actual field deployments over long amounts of time, whether that's been proven, but I do know from some of the work I mentioned, Jaubert and Eric at FSEC, they've done on this load spot system. It does appear that there's at least experimental evidence that they are, in fact, they're more resilient against like cracking. So cracking can still occur, right? That's more of a function of like the mechanical structure of the module, like the thickness of the glass and the frame and everything. But the thing about the shingled interconnects and the kind of the wire connections is it does seem like that when cracks do form, you have less of a penalty, if that makes sense.
Yeah, makes sense.
Yeah.
Here's the question for Kunal. What are the possible reasons for the 2.5% degradation rates in the first year? And is it common to all types of modules?
So this came up in what Chris was talking about too. Light-induced degradation is the main cause of that initial first year of degradation. It's present in P-type modules more than anything else. So a common way that people are trying to get around it is by using N-type modules. And it seems to be present a little bit more in monocrystalline cells as well, rather than polycrystalline cells. So I think the mentality in the industry now is to sort of experiment with these different architectures and cell types and designs to be able to minimize this kind of degradation, whether it's LID or some variation on that mechanism, depending on the type of cell, in order to bring it down. But so far, it seems like across all these different kinds of modules, we're still seeing about 2 to 3% in that first year.
Great. Here's a question for Chris. From your VOC images on slide 61, it seems crystallographic orientation can play a substantial role in the multi-silicon wafer causing VOC. varying from 0.5 to 0.675, while the image of monosilicon wafer shows more homogeneous output. And in the multi-silicon wafer, do you think those dark areas are planes with different orientations or just microstructure defects?
I think most of them, in my experience, the ones that become particularly dark are when you have those dislocation clusters. Those seem to really have a VOC penalty associated with them. I do know that there's quite a bit of work in the literature on this already, and I'm certainly not an expert on the multicrystalline defects, but it does seem like we also notice there's certain grains within themselves that show up darker. And so is that because the entire grain has sorry? So is that because the entire grain is darker, or is it because like the grain boundary, because it's high angle, low angle grain boundary? So you can find a lot in the literature on this, but what we've definitely observed is that the dislocation clusters themselves seem to be the ones that really always just show up dark. And those kind of cells that have less of those, they tend to have the higher VOC, and the PL image seems a bit more homogeneous. Obviously not as homogeneous as a like a CZ wafer though.
Okay, great. Bill, have you tested the effects of water spray on the reliability of Tedlar performance, especially when spray is applied at elevated temperatures and combined with UV or light?
I assume we're talking about water spray from the backside of the bifacial module. Is that correct?
Yeah, I think so.
So no, we haven't. We have done typical weathering type exposures using water spray and UV in a xenon chamber, a typical weatherometer type exposure. We have not seen significant changes in the color or mechanical properties. We've done that mostly on backsheets and films. I don't believe we have done that on bifacial modules.
Okay. So I think we'll get started with the second half of the sessions. Thanks everybody for entering your questions, and maybe we'll get to some more of those at the end of the second session. And our next speaker is Dr. Jennifer Carter, who will discuss PV cell fracture probability and forwarding of PV modules. Jennifer is an associate professor of materials science and engineering. She received her PhD from the Ohio State University, and she specializes in the experimental design for elucidating damage for mechanism in materials under thermal mechanical loading conditions. She has 2 kids and has been riding motorcycles since she was 7 years old. Take it away, Jennifer.
Might as well start with something fun. Thanks, Jen Braid. So I'm going to present today. Most of the work I'm going to present has actually been done by Nick Bosco at NREL. So hopefully if there are any questions I cannot answer, I can phone a friend because he is on the line next. So the goal in the program was to try to elucidate degradation mechanisms in the polymeric materials, the sealants, the encapsulants, and so on and so forth in the modules. And one of the ways that we wanted to do this was under mechanical load. And so we went with a simple loading configuration. Might as well keep it simple. And so we went with 4-point bending analysis. And this is really nice because we can do under load and displacement and see cracking events. And we can also take the derivative of that slope and get changes in compliance. And so what happens here is that we take the load and displacement of each of those cracking events, next slide, and for each experiment, each experiment ends up with a probability of, we run cracking experiments, and we meaning Nick Bosco did, on 30 or so either silicon cells or modules to get a Weibull distribution of the probability of failure. And the goal with the T50 program was to try to understand how exposure lifetimes degraded the performance of these things over time. And so the first step in the project, next slide, was to determine, well, what is the loading that we should do experiment, because of course we don't want them to fail to begin with, but we want them to potentially fail because we want to see degradation mechanisms. So at the beginning of this program, we didn't have our nice, beautiful 4-cell mini module. And of course, you would not want to run failure probability cells to just break them. And so Nick, a series of experiments, next slide, where he ran tests to get probabilities of failure of single cells and the effects of different processing conditions. So he ran experiments on bare tests, and then under each of the different processing conditions, he tested the mechanical, of course, the encapsulant types that we have, and the goal was to use finite element analysis to do a geometric conversion from single cell mini modules in a small scale 4-point bend system with only a 18 millimeter span to conversion to the 36-inch span that we would need for the 4-point modules. And so under all of these loading conditions, next slide, please. Work. So he started with bare cells, both parallel and perpendicular, and he sees that there is a difference in properties with orientation, so processing condition or texture analysis. And then of course, as we add solder to these things, we see a shift from the red curves to the black curves with the addition of the soldering step. Next slide. Of course, we see a similar change with the bifacial shells as indicated by one of the little blue curves that's now hard to see, but that is what it is. But we see a similar orientation dependence and a similar soldering dependency. Okay, and so when we moved from single cells to modules, the orientation dependency continues to show up. And in this case, they were all soldered cells, and we did cells with their EVA or POE. We find that the properties of the EVA and the POE modules are very similar because, of course, the encapsulants have similar stiffnesses at room temperature. So in the conclusions that he found from over 120 fracture experiments, just to get these curves, is that the bifacial cells are more sensitive. And if we are going to come up with a design, we need to account for the orientation dependency that persists as we build modules. So next slide. From there, he took the input parameters from those 120 experiments. We got the Weibull modulus probability of failure parameters. He inputted the geometry and fit the elastic properties of the different materials into a finite element model. So he started with the single cell mini module and fit parameters and geometry to the mechanical performance that we saw from the experiments. And from that, he scaled up the finite element model to account for the 4-cell mini module below, and we get an output of the displacement as a function of applied load and a conversion or M term in the Weibull modulus parameter equation shown below. And so from that work, we end up with the set of experiments, the starting point that we need for the T50 program. So here we decided that we would test the 4-cell mini modules under 4-point bend to different proof loads, which had a prediction of 5% failure for the as received or unexposed samples. And we predicted that if we saw a 10% in the encapsulants in the polymeric materials, that we would end up with either 14% or 35% failure rate, depending on orientation for those things. And so from there, we applied that proof load. And we do this in this experimental setup where we take the graduate students take tau psi EL images before foil point bending under high-res conditions. So this is in a dark box, nice alignment, so on and so forth. And then we move this to the 4-point fixture in the basement, and we run EL images before loading, under peak load, and after. And these are done in the lab under ambient light conditions. And you can see those are up at the top. You see we have a keystoning effect because of the geometry constraints, but we're able to see cracks opening in the middle of the loading sequence of what's going on. Measure of what's happening in this cell. Next slide. And so we saw under the first set of mini modules that we analyzed, we see two different types of behavior. We either see cells that are uncracked, in which case there's no change in the EL image as a function of how the numbers indicate exposure steps. So after step 1, 2, 3, and 4. And so those are 2, 3, 4. And so we don't see any cracking. They didn't have any cracking beforehand, and we see very little change in the compliance value. So if we took the slope of the load displacement curve, that's what we're comparing for compliance values. In the secondary case, next slide, we can see that we have one system in which we did see cracks open is at the top of the loading, but you can see from the load displacement data that we see none of those offsets like I showed on the very first, where we see the crack event during the mechanical testing. And so what that tells me, the combination of the EL image and the compliance value, is that those cracks existed prior to mechanical testing. They are not there because of the mechanical testing. So that's the equivalent of a crack existing and just opening and closing, load and unload. And we see that there is some degradation and some change in the amount of crack due to exposure, but these cracks existed because of manufacturing defects at the beginning of the setup. And so we see again, we don't see cracks during the load displacement experiments. We don't see that jump in offset, and so those cracks existed beforehand. So next slide. So if we take the derivative of the load displacement curve, we can plot the compliance as a function of exposure time. And so we did 4 exposures of heat, and I've forgotten what the FSL slides in front of me, so I apologize. Someone can throw me a lifeline if needed. Roger, can you FSL stand for again?
Full spectrum light. This is the light exposure.
Thank you. You can obviously tell I did not set up the exposure steps. But we could see that for all of the mini modules that are uncracked, we do see an increase of compliance as a function of exposure, which tells me that the polymers are evolving and degrading with the exposure. But of course, the compliance increase is very small at this point. You see that the cracked mini modules, we see a difference in property. We first see this initial drop in compliance as we begin to get cracking and degradation. So you very small changes in compliance to discern different types of failure mechanisms. And we will continue to do this as we move forward through the T50 program and expose all the other samples. I believe that is the end of it.
Great. Thanks, Jennifer. And next we'll hear about non-destructive mechanical property changes of packaging materials from Sameera, Nalin, Venkat. Sameera is a graduate student in the Department of Materials Science and Engineering at Case Western. She joined the SDLE Research Center just in August 2019, and her work in the Toward 50-Year Lifetime PV Modules projects includes mini module fabrication, mechanical studies of mini modules using 4-point proof loading, microindentation of PV module packaging coupons, and degradation pathways using network structural equation modeling. Sameera?
Hi, so today I'll be talking about microindentation studies and some of the results obtained from the PERC degradation project by Dr. Mohan Wong. The study and the method will be continued to be used in the T50 project in the near future as well. The next slide, please. Yeah, microindentation is a non-destructive mechanical method to study the properties of multilayer polymeric systems such as coupons, which have a front glass, encapsulant, and backsheet layers. So the microindentation experiment in this study is done from the backsheet end, and there are two important quantities that are measured. One is the reduced modulus E star, which takes into account the elastic deformation in sample as well as the tip, and creep, which is the tendency of a polymer to deform under load and is a measure of viscoplasticity. And what you see on the left is the deformation magnitude of 2 and 3 layered models from FEM simulations done by Dr. Mohan Wong. And it is important to understand the properties of encapsulant variation during exposures, because an increase in the encapsulant modulus leads to an increase in the cell cracking event or probability of failure, whereas a decrease in the encapsulant modulus would risk in creep. Next slide, please. So coming to the experimental section, there were 12 coupons that were exposed under continuous UV or QUV exposure using different packaging combinations. There were 2 encapsulants used, EVA and PUE, and 3 multi-layered backsheets, KPX, KPF, and PPF. And you can see the structures in the diagram below. And the microindentation apparatus has the capacity to do 2 types of experiments. One is the multi-depth indentation, which consists of multiple loading and unloading steps, and creep, which has only a single loading and unloading step, and then it is held at a constant load for a couple of seconds to achieve steady state creep. Next slide, please. So multi-depth indentation method consists of multiple unloading at 6 different depths. So E star is depth dependent rather than load dependent. So these experiments are load controlled and the depth varies. So if there is an increase in depth, it means there is a decrease in the reduced modulus, and it means that the material is more flexible or compliant. Next slide, please. Yeah, this is the first result from multi-depth indentation. So there are several exposure steps, and after the end of each exposure step, the reduced modulus is calculated from the microindentation data. And what you can see here is at the end of the exposure step of 2,500 hours, there is some change in the E star value, but we would have to do further experimentation to come up with more definitive answers. But as you can see, there is a significant difference between different material types from these 6 combinations. So if we keep the backsheet constant, it is observed that E star of EVA-based coupons have higher values compared with those with POE encapsulant. The next slide, please. And also an experimental model was developed to predict E star using generalized linear model. So this was done at 3 different depths, 5, 10, and 15 micrometers, and delta E star divided by dose was calculated for different packaging combinations. So it is observed that the coupons in which PPF is the backsheet has a higher delta E star by dose value, and that is because of a higher oxygen transmission rate. And also it is evident that there is a slightly positive slope in the case of EVA PPF and POE PPF coupons, and also that POE shows hardening, which corresponds to a lower E star at the end of the exposure cycle. Next slide, please. So coming to the creep trend in coupons, first is what is on the y-axis. It is the normalized creep depth in percent, which is simply the ratio of creep depth and the backsheet thickness. So if you keep the backsheet constant and just look at the trends in encapsulants, there is some kind of difference. There's some kind of creep change due to the encapsulant if the backsheet is kept constant, even though the indentation is done from the backsheet end. And also it is observed that POE KPF and EVA PPF have the least baseline creep depth, but this trend is more pronounced in the case of EVA KPX and POE KPX, the change in creep depth due to increasing exposure. Next slide, please. Yeah, so these are the 2 cases in which the trend is very much evident, and the increase is due to the presence of thermoplastic polyolefin in KPX backsheet. So during continuous UV exposure, TPO undergoes chain scission. There is some change in molecular properties, and hence it leads to a creep increase, and this is confirmed by FTIR results as well. Next slide, please. So the future plan with respect to the T50 project using microindentation is to continue exposure of coupons to about 5,000 hours. Till now, only 2,500 hour exposure has been done for coupons, and we plan to continue it in the QUV chamber and do multi-depth indentation and creep experiments as before. And we intend to extend this procedure of testing coupons to testing mini modules and see how they would compare with the coupon results that we currently have. That's it from my side. Thank you.
Thank you, Sameera. Our next speaker is Jiqi Liu, who will present results from both accelerated and field exposures of double glass and glass backsheet modules in the Towards 50-Year Lifetime PV Modules project. Jiqi is a 3rd-year PhD student in the SDLE Research Center under the Toward 50 project, and her current research is focused on the study of photovoltaic module degradation by performance modeling, image processing, and time series analysis of multiple characterization techniques. Jiqi?
Thanks, Jennifer. Next step, please. Our T50 project has both indoor acetate and outdoor exposure. Today, we would like to show the progress in both. Start with set 1 indoor acetate exposure characterization results. Next page. Yeah. The result I'm going to present today covers the T50 set 1 mini modules fabricated by CSI. The cells used are monofacial multisilicon PERC cells. Here is a figure of the research mini module. We have 4 cells in each module, and they are connected in series. And we have 2 types of encapsulant, EVA versus POE, and 2 kinds of module architecture, glass backsheet versus double glass. So set 1 modules in total have 4 types of different kinds of modules. And for each type, we have 2 modules under each kind of indoor acetate exposure. There are in total 2 kinds of indoor acetate exposure. The first one is modified damp heat. Compared to the standard damp heat, we reduce the temperature to 80 Celsius. And the second indoor acetate exposure is modified damp heat plus full spectrum light. At every step, 1/3 of its exposure time is under full spectrum light. And our research mini module are preconditioned before we start the accelerated exposures. Next slide. Yeah. At each step, we measure the multiple irradiance IV curve for both modules and the cell, and sensitivity curve for each cell, 3 current level EL images and PL image for each module. And then we extracted features from this measurement, and observing how these features changing over time can give us information on the degradation behavior of the module. Right now, for the IV curve, we follow the AEC standard to extract the series resistance from the multiple irradiance IV curve, and then use a DDIV algorithm, which is an R package available on CRAN released by us to extract other IV features from the one-sun IV curve. For the sensitivity curve, which is the red line you can see on the figure, we can obtain another curve called pseudo-IV curve, another curve called effective lifetime versus minority carrier density under log 10 scale. And right now, for the pseudo-IV curve, we extracted 5 features from it. And for the effective lifetime curve, we extracted 4 features from it. These 4 features correspond to the coordinates of 2 special points. One is the peak, another one corresponding to the VMP. And for the EL image, 3 current level EL image, we first will apply image processing pipeline to get the module image from the cell image. And then we extracted the mean and median intensity and normalized busbar rates from the EL image. Georgia, can you click the button? Yeah. And the normalized busbar rates is equal to the average busbar rates divided by the image dimension. So it's a value from 0 to 1. Unless your module experiences very severe busbar corrosion, this number usually is very small, close to 0. And for the PL image, first we still process the image to be cell image, and then we extracted the median and mean intensity. Next step, we're gonna observing how this IV feature changing over time, and do the modeling and get the rate of change to do comparison across different types of modules. Next slide. Yeah, the left figure show how one feature is changing over time for the 4 types of modules we have. Each color is for one cell, and for the points belong to the same cell or crossing different exposure time, we connected them by a line. The black line you see on the figure is a smooth average. And in order to compare the rate of change of this feature across the 4 types of modules we have, we fit linear model to each cell and then extracted the slope and calculate the average and confidence interval to do comparison across different types of module. The confidence interval here we choose is 83.4%. The reason for that is because our focus on this result is do comparison across different types of modules. And the CI confidence interval is not commonly used to do the sample mean test, and that is the job for the t-test. However, if you have enough samples in each group, the sample size is about or larger than 10, and the standard error is within the factor of 2, then you can choose to use this confidence interval to visualize the t-test result with p-value close to 0.05. And right now, for the type that does not meet that requirement, we will mark a star beside the error bar. And right now, the feature we are looking at is the max power extracted from the IV curve, and we are focusing on the modified damp heat exposure first. From this result, you can see the average value did not show significant difference across each other. However, the confidence interval also presents a distribution of this result, which you can see glass backsheet modules has more decrease compared to double glass. And then we check more features and try to find the reason contributing to their power loss. Next slide. Since we are doing modified damp heat, this exposure condition usually will accelerate corrosion problem happens to the module. So the first feature we check is the series resistance. However, the result shows that their average value has no significant difference. And considering the confidence interval, it shows that POE has more RS increase compared to EVA. So this RS shows totally different module type dependency compared to max power. Next slide. Another feature is closely related with corrosion problem is the normalized busbar base. And from this result, we see double glass modules do not experience busbar corrosion, but glass backsheet modules do. more apparent in the glass backsheet plus EVA type. And this result means the corrosion problem is very located to the busbar region for the glass backsheet plus EVA type. Next slide. And now we move our focus to this max power extracted from the pseudo IV curve. You can treat this max power as the one without the influence of series resistance. From this result, we can see after we remove the RS influence, double glass modules has no sign of power drop, which indicates that corrosion problem is a major problem of the double glass modules power loss in the modified damped heat. And compare this result with what we get from the max power extracted from the IV curve, the position for glass backsheet plus EVA, it does not have any change, which indicates corrosion problem does not contribute much power loss for this type. However, for glass backsheet plus PUE, you can see this number, it reduced from -0.4 to about -0.1, which indicates that about 75% of power loss for glass backsheet PUE is contributing by corrosion. Next, we're gonna check more features and try to explain the power loss in glass backsheet plus EVA and the remaining 25% of power loss in glass backsheet plus PUE. The first feature we check is IC short circuit current. And we found that compared to double glass modules, glass backsheet modules has more apparent IC decrease, especially in the glass backsheet plus EVA. And we believe this is one important reason contributing to its power loss. Next slide. And the next feature we check is the shunting resistance. Shunting resistance is very difficult to extract accurately because of very flat IC region. However, from this figure, you can see a very apparent difference in trend for the shunting resistance in different types of module. More apparent for the glass backsheet PUE, it has a very significant decrease of shunting resistance. And we think this is like the major reason contributing to its remaining 25% power loss. Next slide. In addition, we found that a lot of features extracted from the sensitivity curve has decreasing trend for all types of modules. This indicates that all types of our modules experience some degree of recombination problem. Here, I choose to show the result of the effective lifetime corresponding to the VMP point. And you can see the average value did not show significant difference. However, the CI is lower for glass backsheet plus EVA compared to others, which maybe the recombination problem is another contributing factor to this type of the power loss of this type of modules. Next slide. Here we summarize our finding for mini modules under modified damped heat. Even we found the average value of the rate in max power obtained from the IV curve did not have significant difference across different type of modules, but the reason contributing to its power loss is quite different. For the double glass module, the major problem is corrosion. And for glass backsheet plus EVA, the major problem is IC decrease, and it probably has more recombination ICO compared to others. And for glass backsheet PUE plus PUE, the major problem is corrosion, but it also has contribution from the shunting decrease. Next slide. Now we move to another authority exposure we have, modified damped heat plus full spectrum light. This exposure compared to modified damped heat, at each step, 1/3 of its exposure time is under full spectrum light. And first, we look at the max power extracted from the IV curve. The result shows the average value has no significant difference. However, the CI for glass backsheet plus PUE is lower than other types. Next slide. Now we go through the same process to try to find the reasons contributing to this power loss. And the findings are very similar with what we found in modified damped heat, but we have more confidence that the glass backsheet plus EVA has more severe recombination problem compared to other type. Because right now, if you look at the effective lifetime corresponding to the VMP point, that confidence interval is no longer show overlapping with others. And we also found that glass backsheet plus EVA has slightly shunting decrease. This result agrees with our understanding of the exposure conditions. Our full spectrum light, the average light intensity is about 420 watt per meter square, and it contains very limited UV, and this exposure condition accelerated recombination as a current source instead of accelerate the aging of the encapsulant, which will usually present as an ISC decrease. Next slide. That's all findings we have for the indoor accelerated exposures for now. And here is some of our future plan. We are currently working on to improve the stability of our IV measurement. And we want to study more of our PL image about the defects spatial distribution. And we would like to dig to more about the ISC decrease and shunting decrease of the two types of glass backsheet modules we have. And right now we are about to start the Site 2 indoor accelerated exposure very soon. As Site 2 modules have bifacial multisilicon PERC cells, and the backside encapsulant is opaque type. And by comparing the Site 1 and Site 2 result, it's gonna help us to locate the degradation behavior dependency more clear. Next slide. That's all we have for the indoor part. Now we move to the progress we have in outdoor exposure. Next slide, please. Yeah. In total, we have 32 outdoor mini modules. They are all fabricated by CSI. And these 32 modules belong to 16 tabs. So for each tab, we have 2 mini modules. And these 16 tabs covers modules with monofacial versus bifacial cell, encapsulant of EVA versus POE. And for the backside encapsulant, we have more kinds. It could be UV cutoff, opaque, or transparent. And we have double glass and glass backsheet modules. And we also have 2 different types of modules, monofacial module versus bifacial module. Monofacial modules is the Site 1 to Site 3, and bifacial modules is Site 4. For the glass backsheet bifacial modules, we have the backside encapsulant is the UV cutoff type, and the backsheet is the clear backsheet supplied by DuPont. Next slide. Yeah, these 32 modules are installed on a fixed track on our sun farm. And right now we use the D-Star control unit and the load unit to recording the 1 minute max power and JHI and 10 minutes IV curve. And we use a Campbell Sound data logger to recording the 1 minute POA and the module temperature of these 32 modules. The exposure start on April 28th. So right now we have time series data about 3 months. This short time series is just too short for construct degradation study. But what we can do is do an initial power output comparison since we have so many types of modules. And our POA sensor got installed 1 month late compared to the start of the exposure. So right now we use the GHI as the irradiance data source for further data analyzing. Next slide, please. Yeah, what we see right now is the module temperature distribution and the irradiance distribution of both GHI and POA. The median module temperature is about 40 Celsius, and the median irradiance is about 700 watts per meter square. Next slide. Now we apply a method called XPX plus UTC to our time series max power to get daily predict max power at reference conditions. This method, UTC, represents universal temperature correction. And this method first do a low irradiance filtering, and then get the temperature coefficients by fit the linear model of max power versus module temperature using the data range very close to the reference irradiance range. And then it do a temperature correction to all the max power using the temperature coefficients it obtained from the last step. And then for each day, it fit a model of the temperature corrected max power versus the irradiance. And finally, it inputs the reference irradiance into the model of each day to get the daily predict max power. And for each module, we have data about 90 days predict max power, and this data can be used to form a distribution. Here I show an example of one module. Next up, we're gonna compare this distribution across different variation we have in modules. Next slide, please. The first comparison we do is modules with bifacial cells versus modules with monofacial cells. The results show their average value has a significant difference. The one with bifacial modules has higher power output. The difference is about 4.3% in power. Next slide. Next comparison we do is the modules with EVA encapsulation versus the modules with PoE encapsulation. The average value shows a significant difference, and the modules with EVA encapsulation has higher power output, and the difference is about 2.6% in power. Next slide. Now we are looking at the comparison across module architecture, glass backsheet modules versus double glass modules. These two, the average value does not have significant difference. Glass backsheets, the average value is slightly higher, but the difference is within 1%. Next slide. The last comparison we do is bifacial module versus monofacial module, and the result shows the average value has a significant difference. The bifacial module has higher power output. The difference is about 2.6%. And just for curious whether the bifacial glass backsheet module can have similar initial power output compared to double glass module, we take out the 4 types of bifacial modules we have and plot the CI here. And from this result, you can see for EVA type of glass backsheet bifacial module, it has a similar power output compared to double glass module, but is slightly lower in the PoE glass backsheet modules. Next slide. That's all our current results. Here is some of our future plans. We're definitely going to continue our exposure throughout the whole project period or even longer. Once we got the time series data slightly longer than 1 year, we will start to do regression method and study the degradation behavior of it, and also involve the time series IV curve, since it can give us the change in the IV features for located the degradation mechanisms. And recently we have a good package came out for other IV curves analyzing. It can, that package is called sensibility, and it can be used to construct the IC VOC curve and do loss factor calculation to compare the change in the IV features to the power basis. And once we got the indoor model and outdoor model, this project also contains a part to do indoor-outdoor cross correlation. That's all we have for T50 result right now.
Great, thank you, Jiqi. And again, please enter any questions in the chat for the second Q&A session, which will be after this last talk. Our final speaker is Greg Horner of Tau Science, who will present instrumentation and tool PV research. Did his PhD research on 3.5 materials characterization and has spent time in both the semiconductor and solar industries developing machines for process control. He started Tau Science in 2008 to focus on PV test and measurement, and the team has worked on a variety of applications spanning silicon, 3.5s, and thin films. Take it away, Greg.
Okay, thank you, Jen. Okay, I think we can jump right to the next slide. This presentation is more of a list. It's not a coherent study of any particular failure mode, but we're just presenting a list of machines that we have developed in conjunction with others or on our own over the past 12 years. And it's just so that the community knows that we exist and these products exist, and you might contact us in the future if you do have a new project that requires something like this. So in general, we first develop a product for R&D labs, and then if there's a need, then they may be boiled down to a simpler, faster machine that can be used in the factories. And we just kind of do this again and again, and every once in a while something is adopted for inline metrology. Okay, next slide. For R&D, the machines often are about the size of a standard US refrigerator, and it's a manually loaded machine. The laser enclosure, if it uses lasers, is all integrated into the box, as are all of the electronics. The different techniques that we have incorporated include Pulse QE, which is an LED-based QE system. It's very fast. You can acquire the whole EQE and reflectance spectra in about 2 seconds. And that's fast enough that you can mount a stage in there and you can actually map the EQE and reflectance spectra. So that's some of the work that you saw from the Davis group in Florida. IRIS is an infrared inspection system. It uses long-wave infrared cameras to detect hotspots. If it's a cell, then the test only takes about 300 milliseconds because they heat up so quickly. If it's a module, it may take 30 seconds because of that high thermal mass of the glass. But it's possible to do it on either cells or modules. Pixel is a PL and EL imaging system, and it's also got a kind of a math capability built in so that you can take your stack of images and do math and extract parameters from them. In the lower right is a new one, and that's the time resolve photoluminescence system. So that takes a series of high-speed PL images after a laser pulse. And so we can actually, for every pixel in the image, plot out the PL intensity versus time as it decays away. That's a new one. We've only shipped one machine, and we'll start kind of rolling that out in the next month or two. So that's a way to study not just the lifetime of a cell at a single point, but you can actually get the entire image of the lifetime. Okay, next slide. Great. So sometimes we boil the technique down to a desktop. It may be to lower the cost and make it more accessible to universities and smaller budgets. And sometimes it's for the purpose of putting it in line. So this is one example. This is a pulse QE system. It's using LEDs, just like the one we described in the previous screen, but we're not focusing them down to a spot. We're actually illuminating the whole cell. So you can go up to a 210 by 210 cell. There also is a non-contact version of it where we do what we call ELE. So it's electroluminescence, but it's a spectroscopy used by varying the incident wavelength and monitoring the electroluminescence signal. So if we hit the next button, I think we can play this next one. It kind of should pop up a movie. And if you hover over it, I think we can find the go button for the movie. We'll see if this works. Well, maybe not. That's okay. Yeah, we'll skip that then. That's no problem. So the other thing that we do is we have R&D components. So for instance, for the Case Western group, they needed a variety of components to finish their coupon tester or their mini module tester. So we build LED light towers. These are liquid cooled LEDs for high brightness. The DC control systems to either apply cell bias or light bias, temperature controlled chucks. And the thing that ties it all together though is the pixel control software. So if you hit the arrow 1 or 2 times, I think you'll see a few more pictures appear on this slide. So there's an example of a chuck that we would design for any number of bus bars. And then now the pixel software starts to appear. So this is an image from our GUI, and one more click will bring a couple more images in the lower left. Okay, and this is the really unique thing, is the ability of the customer to do post-processing. So they may write a recipe to acquire 12 different images in one swoop, and it's a variety of could be filters in front of the camera, EL currents, currents driven through the cell, as well as illumination conditions using the lasers or LEDs. And then they're free to write their own algorithms in any language, post-process that stack of images, and then hand the results back to the database. So in this case, it's a very clearly they're just looking for cracks. They count the cracks and hand back a processed image at the end of it. But you can do anything. All of the biased PL techniques are accessible through your own code. Okay, next slide. Okay. As we scale up, when we talk about working on modules and mini modules, the machines naturally get bigger. So here's a picture of a mini module scanner that we built. This is actually a QE system, and there's an overhead gantry that moves the QE head around over the mini module. I think if you hit the arrow one more time, we might see one more example. So this is inside an even larger system where you can load an entire 2.2 by 1.1 meter module. This one's out at NREL now. So this is a way to measure QE at any point on any cell in a module, or you can map the whole module. So that's an example of QE measurements on modules. We do a few more techniques though for both modules and mini modules. So we'll go to the next slide and see some of those. Okay, this was done by Steve Johnston recently out at NREL. So this is called nickel, sometimes non-contact EL. It's using a really neat feature that we're illuminating one portion of a cell. And if you looked with a camera in that region, you would detect what you would call a normal PL image. But instead of doing that, we are looking for emission from non-illuminated regions of the cell. So we hit it with light in one half of the cell, and we collect the EL from the other half of the cell. And then we flip. We illuminate, we flip the illumination and the collection, and then we stitch the two halves of the image together, and you've got an EL image without ever touching the module or driving current through it. So actually, if you look at that picture, you can see the two leads to the module are just kind of hanging out the top of the module. There is no power supply connected. This scanning system moves the box around in front of each cell. It takes about 4 minutes to scan the entire module. The data collection is really fast, about 30 milliseconds to collect one image. But it has to move to the next cell. We use in-gas cameras. They don't have terribly high resolution, but when you do it on a cell basis, that results in a 16 megapixel image for the module. It's useful both indoors and outdoors. And when you are working indoors or at dusk, there's one really strong advantage to this technique. That is that when you look at a normal module EL image, there's a strong background component. There's a background glow that you just can't get rid of, and that's all the surrounding cells. They're all emitting EL. The light bounces or light pipes through the glass and gets into the neighboring cells. So it's just impossible to remove that from your EL module images. When you do this technique, then you're really only driving one cell at a time. The neighboring cells do not push out a background glow. So you get really high contrast EL images. So the software will stack up anything up to a 32-bit image by taking multiple frames and stacking them. So the next slide. So the dynamic range of the images is really what's exceptional in the technique. And if you hit the arrow one more time, I think we'll just zoom in a little. So the images are quite high quality, and the dynamic range is much better than a conventional EL. Okay, I think we can go to the next slide. The next thing we need is a good GUI so that you can do something with this information. So whether you take your image using a conventional EL or the non-contact EL, we have recently rolled out a software control program that allows you to classify the defects. So this was working with Bright Spot Automation, Andrew Gabor, and Will Hobbs at Southern Company, and the group at PVEL. We kind of came to a conclusion of what it should contain. So it's the EL image appears on screen, no matter how it was collected. The operator is free to tap on any cell that looks suspicious. They get a zoomed in view, a detailed view, and then they can classify the defects using the touch screen, be it a single crack or a dark cell or anything in the list. So that's the list that was generated by Will Hobbs. Let's go to the next screen. So if the operator does this, what's happening is the modules are getting graded on the fly. So if it has a certain number of single cracks or a certain number of double cracked cells, those count against a total score. And eventually, according to the prescribed criteria, that module is a failed module. So we have a way of screening out modules even before they're put up on the rack. So this would be a pre-installation screening application, but you can use the data for however you wish. You could track a single module over time and come back to the database again and again to see how it has evolved over time. And we have reporting systems that can summarize the results. If you've measured tens or hundreds or thousands of modules, you just push the button and it'll generate a large report containing all the thumbnail images as well as the summary data. Okay, next slide. All right, I think we'll skip this one in the name of time. There is another technique called EL sweep. It's a neat way to extract cell parameters out of a module, so feel free to contact us if you'd like to discuss that. It's really been driven by the UCF group. I think Dylan Colvin has the most recent paper on that, the Davis group, as well as bright spot automation. Okay, next slide. All right, so the last one is what's currently happening, and that's daytime EL. So we finally found a combination that allows us to use a silicon camera at high noon outdoors doing EL. This was possible before with in-gas cameras and things like modulation or synchronous modulation, but I think we finally got it working for high resolution silicon cameras. It's still challenging, so it really only works on monosilicon high efficiency modules. If you bring a 5-year-old poly module, it probably does not have the luminous efficiency for us to extract the signal from the background of the sun. And you can see even in these images that it's a grainier looking image than what we were looking at earlier. So it's still a challenging technique, but we are doing beta testing now, so feel free to contact us if there's interest there. Okay, I think that was it. Feel free to contact us at Tau Science if you have any questions.
Great, thank you, Greg. And we'll just do a couple of questions for the second session. I know we're at 10 o'clock now, so let's just jump into those questions. Here's a question for Sameera. It says, usually microindentation creates a plastic deformed zone deemed as a destructive method, but you mentioned your method is non-destructive. So how did you do it? And how could you please elaborate on zigzag strain stress curve, and how did you extract the modulus from that curve?
Hi, so those are a set of great questions. So I'll answer one by one. So this is a non-destructive method because we don't use a very high load for, this study was not done by me. It was done by Dr. Mohammed. So she used a single depth indentation to study at which load there would be plastic deformation and at which load there wouldn't be plastic deformation. So she found out that at 10 newtons there would be plastic deformation, but somewhere around 1 or 2 newtons there wouldn't be any type of deformation. So that way this method is non-destructive. And it is not exactly a stress strain curve that I showed in the slide, but it is a load versus depth curve. So it is just to highlight that there are multiple loading and unloading steps. So we don't extract any information from that curve. It's just to highlight that it is a multi-depth indentation. And so this method is still under development. Like, she has developed the method, but we still hope to make some modifications. So there's no standard as such to perform this test yet, at least from industry point also. But Dr. Jennifer Carter can explain in further details about the analysis part and how she modified the Oliver Farr method to calculate E star for microindentation.
Jennifer, do you want to weigh in on that?
I don't know that I need to weigh in on it now, but yeah, so the Oliver Farr method was developed for extracting elastic modulus and strength behavior from nanoindentation experiments to effectively get pseudo single crystal behavior from these samples. If you notice in Sameera's slide, the zigzag pattern is load time. Placement data has a zigzag, but they completely overlap one another, which tells you that the test is still in the elastic regime. You're getting no cracking or plasticity in the case. If you want, I can share with you the original Oliver Farr method and used for application of the nickel alloys. So Mahong's trying to use this for a composite structure, which is why we have E star, and it's not the elastic properties of any one material, but the whole stack together.
Okay, great. So yeah, if the person who asked that question wants to reach out to Jennifer for more information on that, she would be happy to share that with you. We have a couple of questions for Jiqi. The first one is, what is the reason for the ISC increase in the double glass modules after damp heat testing? And that's from Paula Sanchez Freire.
Thank you. Roger, can we go to that slide? I think it's slide number 117.
117?
Yeah. Yes. So from this one, you can see the ISC increase for double glass module is mostly due to the equipment system shift from step 0 to step 1 for double glass module. After step 1, the trend in double glass module for IC is very stable. It's almost a flat line. And right now we are working on improve the protocol for our IV measurement. Hopefully for the site 2, we're gonna have more stable result for all the IV features we have in from the IV curve.
Okay, and another question for Jiqi is, for outdoor exposures, you showed that modules with EVA had higher PMP compared to POE. What do you hypothesize is the reason for this? That's from April Jeffries.
Thanks for the question. First, we know our modules, all the outdoor mini modules use the same batch of cell and consider the influence of encapsulation to cell as for its initial performance. I think it's most likely due to some slightly different in the encapsulation transmission, which will influence the IC directly. But right now, we don't have the result came out from the IV features. But you can see our data acquisition includes a 10 minutes IV curve. So once the result came out, we can easily confirm that which feature caused that difference and link that with the encapsulation property.
Okay, great. So I think now we'll close the session. Thank you again to all of our speakers and to everyone for your participation in today's webinar. We'll make the slides and a recording of the event publicly available on the SDLE website, which is sdle.case.edu/T50webinar. And if you have any additional questions or feedback on the content presented today or future directions of this research, please email Roger French at rxf131@case.edu. And thank you again for your engagement and have a great day.
Thank you all and stay healthy.